Hello, ladies and gentlemen. Welcome to our first nuclear physics lecture. Well, I'm going to promise to keep this really short, so let's get right into it. Now, what do you know about atoms? Well, in the past, people thought that atoms were like solid spheres, okay? That's called the Dalton model of the atom. There's atoms that cannot be broken into smaller pieces. Actually, the word atom means atomos, means indivisible. It cannot be divided. Well, after that, they discovered that there were electrons inside the atoms. So J.J. Thomson in 1897 showed that the atom had something called an electron inside. So it's not indivisible, and they tried to figure out what else was inside the atom. So after discovering the electron, J.J. Thomson said the atom is like a plum pudding. Now over here you can actually see a plum pudding, sometimes called a Christmas fruit cake that some people eat during Christmas, especially the British, and it's very delicious. Okay, it's got lots of like raisins inside it. Okay, so probably fascinated by plum puddings, Thomson said that atoms were also like plum puddings. Okay, so obviously this model was also wrong because we know that it didn't work. Now, how do we prove that something is wrong? Basically, you got to do an experiment. Okay, so a professor called Rutherford, all right, or Rutherford, depending on how you pronounce it, decided to put Thomson's plum pudding model to the test by shooting alpha particles through a thin gold foil. Basically, when you shoot alpha particles through a thin gold foil, if J.J. Thomson's model is that the atom is a plum pudding, these alpha particles will go right through like bullets. Okay, so they're gonna just like go through. This is if the plum pudding model is correct. So what do you think? Is the plum pudding model correct or wrong? Are atoms really so delicious like Christmas cakes? Obviously not true. Okay, the actual observations was that most of the particles went straight through or were scattered through very small angles, but some of them bounced right back. And this is impossible if the atom was a plum pudding, which was very soft. Okay, so here's the results of the experiment. Some of the particles were scattered, all right, over 160 or 180 degrees. So you might be at this point, you might be thinking, what are alpha particles? And what is this alpha particle scattering experiment? I don't really understand. So what better way to understand than to watch a video? Okay, so let's take a look at this video over here. I hope you can see it. Now, inside this little chamber with the grills is a piece of radioactive material, americium. Okay, and these are little alpha particles shooting out of it. Now you can see it because in this special chamber called a cloud chamber, there's alcohol vapor. And when the alpha particles pass through this vapor, they ionize the vapor and cause condensation to happen. So these little alpha particles are all shooting little clouds, leaving little cloud trails behind them. So now I'm going to talk about the alpha particle scattering experiment. Now over here in this different cloud chamber, you can see that there's americium and it's shooting out alpha particles as well. Now this cloud chamber is different. It doesn't always work all the time. It only works when it's pressurized or depressurized. Okay, so you can see the americium shooting out alpha particles. Now the alpha particles are always coming out, but the cloud chamber only detects it when it's activated. So here we place a thin gold foil in front of the americium. Can you imagine the alpha particles keep bombarding the gold foil? Now, look closely. Okay, let's play that again. The alpha particles are going to shoot right through the gold foil, but I want you to take a look at the upper right corner over here. Okay, so the alpha particles will shoot. Do you notice that one of the alpha particles actually bounce backwards off the gold foil? So you can see that alpha particles, most of them went straight through the gold foil without any deflection. One of them bounced right back. And this is what is meant by the Rutherford gold foil experiments. Alpha particles hit the gold foil. Most of them go straight through, but one of them bounced back. All right, a few of them bounced back. Now, what are the results of the alpha particle scattering experiment? So now we know that the atom is not a solid ball, like a billiard ball, and neither is it like a plum pudding. Okay, so since most particles pass through the atom without deflection, So the atom consists mostly of empty space. This is one of the results of Rutherford's experiment. Now, next, a small fraction of the alpha particles are reflected through large angles. That means that there must be something inside the atom concentrated in a small region of space, which is very massive, okay, and it contains all the positive charge of the nucleus. Now, let's take a look. All the positive charge, this word must be there, and is also most of the mass of the atom is contained in the nucleus. So Rutherford was the one who figured out that there is such a thing in the atom called a nucleus. Now, later on, they discovered that the nucleus is made of two types of particles. The first type of particles found in the nucleus is a proton, and the second type of particle found in the nucleus is a neutron. All right. So the nucleus contains protons and neutrons, collectively referred to as nucleons. Now, please don't get confused. We're going to use a lot of words right now. We already know nucleus. All right. We already also have neutron, and then we also have nucleon. All right. Now, the nucleon consists of both protons and neutrons. Okay. Okay. So the nucleus is very, very small compared to the size of the atom. Please remember these two numbers. Okay, you got to remember this. The atomic diameter is given a symbol angstrom, angstrom. All right, and the nuclear diameter is 10 to the power minus 15. All right, value of that. Okay, so 99% of the mass of the atom is in its nucleus. Now, these are the parts that make up the nucleus. Okay, electron, proton, and neutron. Now, please note that the neutron's mass, although they rounded up to 3 sig fig, is going to be slightly higher, slightly more massive than the proton. All right, so although you can't see it because the there's not enough decimal places given in this lecture slide. Okay, but please note that the neutron is slightly more massive than the proton. Okay, let's move on. So, a simple model of the atom was then developed. Okay, the atom is supposed to have a central positively charged nucleus. It's very, very small but very, very massive, made up of positive protons and neutral neutrons, and the electrons revolve around the nucleus in orbits. Now, this is now an outdated model, which we now know is inaccurate. Okay, so this was the model at the time that was proposed after Rutherford's experiment. Let's move on. Okay, so let's talk about how nuclides work. All right, now you may have seen a symbol of a nuclide, such as, let's say, carbon 14. Now I'm going to teach you guys to be nuclear scientists now, okay? So here is a nuclide called carbon 14. Now, the proton number is uh, the number of protons in the nucleus, all right? So this is the proton number. And the nucleon number or mass number A gives a total number of nucleons, protons and neutrons in the nucleus. So this is the nucleon number. Now, how do we get the neutrons number? So the number of neutrons will be equals to 14 minus 6. This will be 8 neutrons. All right. Okay, so this is 8 neutrons. So the nucleon number at the top is not the number of neutrons. Okay, you must take 14. The top number minus the bottom number gives you the number of neutrons. Okay, so in general, the notation to represent a nucleus is, okay, A, X, and Z. So you can easily remember it as going from A to Z and X in between. All right, so A is at the top, Z is at the bottom, and X is in between. Now let's take a look at checkpoint one. All right, the conventional notation for the iron nuclide is 5626 Fe. State the number of protons, 26. State the number of neutrons, 56 minus 26 is equals to 30 neutrons. Total number of nucleons in the nucleus is 56. Okay, so that's our checkpoint number one. Now let's take a look at isotopes. Now, isotopes are atoms that have the same number of protons but different number of neutrons. So let's take a look at two famous isotopes, which are carbon 12 and carbon 14. All right, so I would say that the two rows of isotopes over here, you must memorize these two rows of, whoops, How do you spell memorize? Memorize. Okay, memorize these two rows of atoms. Okay, so our famous one is hydrogen. The next level up is deuterium, and the next level up is tritium. Now, and over here we have carbon 12 and carbon 14. Now, of course, carbon 14 is radioactive. What does radioactive mean? Well, we'll find out in the next lecture. Okay, so can you separate out these chemicals by chemical testing? No, it is not possible to separate isotopes. The isotopes have the same chemical properties because the number of electrons in the atom is constant. They have a same constant number of electrons, so there is no difference in their chemical properties. In that case, how do we separate out the atoms, the different atoms of carbon 12 and carbon 14? Now, the isotopes have different physical properties. What do I mean by different physical properties? Well, you see, the main difference between carbon 12 and carbon 14 is the mass. Carbon 14 is heavier than carbon 12. So the only way to separate carbon 12 and carbon 14, or the main way to do it, is by doing mass spectrometry. So we separate out the elements based on how heavy they are. They also have different densities because they form the same chemical compounds like carbon, graphite, or carbon dioxide, but they have different densities. Carbon 14 is much more dense than carbon 12. So you can actually separate it out using a centrifuge. By spinning it round and round really fast, the heavier carbon 14 will sink to the bottom and the carbon 12 will rise to the top. Okay, so these are isotopes. Now, let's talk about how heavy a carbon 14 or carbon 12 atom actually is. All right, so let's go on to our next page, and this will be our last topic, 2.1 and 2.2. Then after that, the lecture will be over. Okay, so how do we find out what is the mass of a particular nucleus or atom? Okay, atomic masses are usually expressed in the terms of the unified atomic mass unit. Now, one unified atomic mass unit is 1/12 the mass of the carbon 12 atom. Why is this chosen? Okay, I'll tell you later because it's really easy to use this unit once you know how to do it. So let's take a look. One unit would be 1.66 times 10 to the power of minus 27 kg. So now we can actually use this unit, okay, to determine, roughly speaking, what is the mass of an atom. So let me just give you a rough mass, okay? So roughly speaking, rough estimation of the mass. So uh, let's say what is the carbon 12 nucleus mass, okay? The carbon 12 nucleus mass will be equals to 12 units. That's all, 12 units. So putting in a calculator, you get 12 times 1.66 times 10 to the power of minus 27. This will be enough to give you a rough estimation of the mass, okay? What about carbon 14? Well, carbon 14 mass of the atom will be 14U. What about uranium 235? Uranium 235 mass will be 235U. Now, these kind of rough calculations are enough to give you a rough estimation of the mass, correct to maybe 2SF, okay, 2 or 3SF for rough calculations. Of course, later in the tutorials, there'll be much more detailed calculations needed that need you to go into 5 or 6 decimal places, and that in that case, you've got to use the more accurate numbers, okay? So the unified atomic mass is going to be able to give you roughly, very quickly, the mass of a particular nuclide or an atom, okay, correct to about two sig figs, okay? And we shall stop here for today. I told you that it was going to be a very short lecture, and I delivered a very short lecture. So I'll see you again in real life, okay, next week. Bye bye.